we've talked about the area between the pole and polar function, which is kind of interesting. This horizontal axis is called the polar axis, which I didn't realize. Or not the polar axis, it's the pole. The pole is considered the entire axis. Yeah, I always thought the pole was the center, the origin only.
Yeah.
But the problem we're about to look at is what happens if you take a circle and you can revolve that around two different axes. You can revolve it around the polar axis, or you can revolve it about the line theta equals pi over 2.
Okay.
I guess you could revolve it about all kinds of thetas. I mean, you shouldn't be limited to those two. But the polar axis, I guess, is theta equals 0. And in other words, similarly to being able to revolve stuff around the x-axis and the y-axis.
Okay.
Clearly, if we revolve this around the polar axis, we would have a sphere. I think. Yeah? Yeah, I think so. If we revolve it around the pi over 2 theta axis, we get a donut shape. It's called a torus, and it's actually called a pinched torus because there ends up not really being a hole in the middle. If you imagine a donut with the insides touching, that's what you would have if you rotate this thing about the vertical axis. The equation for the surface area of such an object, there's two of them. One is the surface area equals 2 pi times the integral from alpha to beta.
This is for a pinched torus?
No, this is just for any object of revolved around, hold on a minute. Yeah, let me write the equation out first and then let's talk about it.
Okay.
Remember, f of theta is always r. And this is similar to arc length in that we have the square root of f of theta squared plus f prime of theta squared.
Okay, right, I remember that.
In other words, this part here was part of our arc length. And that's exactly what arc length is.
Okay.
It's the square root of r squared plus dr d theta squared d theta. And it goes from alpha to beta. So this makes sense when you think about how we got surface area under the rectangular coordinate system. It was a function of arc length. I'm trying to think about that for a second here. And, oh yeah, we had to use those things that I can't even remember the name of them. Rondons or something like that. But anyway, this is very similar. This deviates from arc length by 2 pi f of theta sine theta. Okay, and that's if we're revolving about the pole. revolving about, let's call it theta equals 0. And if it's revolving about the vertical axis, the equation is identical, except instead of sine theta, it's cosine theta.
So this is, okay, let's see. Okay, so this is the pi over 2 axis?
Yes.
Okay.
That's revolved about pi over 2. Theta equal pi over 2.
Okay.
Now, they don't go through the derivation of this thing. Let me see what they say. They say, the polar coordinate versions of the formula for area of surface of revolution can be obtained from the parametric versions given in theorem 10.9. And then using the equations x equal r cosine of theta or y equal r sine theta. Okay, so they get these by looking at the area of surface of revolution for parametric equations.
Oh, Dave, I wanted to ask you about notation. It's when you have like under the square root sign there, f of theta squared. That means like that would be r squared, right? I mean.
Yeah, and actually I don't have it written correctly. I should have parentheses. In other words, it's f of theta being squared, not theta being squared and taking f of it.
Okay, and yeah, that's what I was wondering. How would they usually annotate that? Is that with the brackets?
Same thing over here for these two. They do have brackets around them.
Oh, I see.
I just didn't notice it when I was writing it, so I didn't put it in. Yeah. All right, so probably the best thing we can do is go through their example of, they only have one example of finding area of surface of revolution. And we're going to rotate it like that. And the drawing they end up with showing this object looks like a donut. Since we're rotating it about pi over 2, we're going to use this equation. So it's going to be s equal 2 pi. Let's leave these for a second. This equation, incidentally, is r equal cosine of theta. R equal cosine of theta is a circle. Now, this is where it gets a little confusing. A to B is what you have to do to be able to draw this circle. In other words, we want to distinguish between alpha and beta here and these axes that are being revolved around.
Okay.
We're revolving it around the pi over 2 axis, but that doesn't give us alpha or beta. Alpha or beta comes from what you have to do to draw this circle. Well, let's see, when I'm at 0, I'm at there. When I am at pi over 2, I'm back to there. In other words, I draw this circle this way.
Oh, I see. When you're okay.
And when I go from pi over 2 to pi, I'm back to here. So I draw the bottom half. So my alpha and beta is 0 to pi. And their little note here is that be careful about double tracing it.
Okay, let's see.
Alpha and beta is what is required to trace exactly once. And this circle is traced out when we go from 0 to pi. The fact that we're revolving it around the pi over 2 axis is taking account of the cosine of theta over here. Taking account for that. So that really doesn't have anything to do with alpha or beta.
What accounted for it? The cosine in the equation?
Yeah, in other words, the top equation is when you revolve your two-dimensional object about the polar axis, and the second equation is when you revolve it about the vertical axis, or the theta equal pi over 2 axis.
I see.
Okay, but that's not where alpha and beta come from. Alpha and beta come from creating this two-dimensional circle. Not the donut, but the circle. Okay, and now f of theta is cosine theta times cosine theta times the square root of cosine squared theta. The derivative of cosine is minus sine, so plus minus sine of theta squared, all of which is equal to 1. So we have, well, this part. In other words, cosine squared theta, this becomes plus sine squared theta.
Yeah,
Minus sine. What's that?
I was just trying to catch up here. Now let's see. We got cosine of theta. Okay, that's the.
That's f of theta. That's this first one.
Right.
And then times the cosine of theta that follows.
In the equation. Okay.
Times the square root of f of theta squared, which is cosine squared of theta.
Okay.
Plus f prime. Well, what is f prime of theta? It's negative sine theta.
Okay.
So we're going to square that. And when you square negative sine theta, you get positive sine squared theta. So now what we have under the radical is cosine squared plus sine squared. That's 1, always. So now our length becomes 2 pi times the integral of cosine squared theta d theta, going from 0 to pi. Here, I'll bring it back in here. Okay. Just wanted to create a little room.
Okay.
Okay. Now let's go over and remember our trig identities. Cosine of 2 theta, the double angle identity, is equal to cosine squared theta minus 1. And that's 2 of these, if I remember right.
So 2 theta, 2 cosine squared theta minus 1.
Therefore, remember that when we are integrating trig functions that have exponents, we have what are called power reduction identities, which allow us, in other words, this is tough to integrate, cosine squared theta. Can't use the power rule because there's no sine theta next to it. So the way I integrate cosine squared theta, or for that matter, cosine to the 4th theta, or whatever, no, I take that back, only cosine squared theta. would be to convert it using that. So I get cosine squared theta equals cosine 2 theta plus 1 divided by 2. Now, this is very easy to integrate. In other words, integrating the cosine of 2 theta is just sine of 2 theta divided by 2. So we're going to use that, and now s becomes, and I'm going to take this 1/2, this bottom denominator of 2 outside the integral sign, canceling out with 2 right there, so it becomes pi. I'm still going to go from 0 to pi, and now what I have inside is 1 plus cosine 2 theta. D theta. In other words, that's the same as this identity up here, only I took the denominator outside the integral.
Oh, I see. I better write this down in a couple steps here. So,
in other words, these two things are the same.
Right. So we'd really, initial step would be 2 pi taken out. And then, okay, 0 to cosine. Shoot, let's see. You
could really just go from this step straight down. You don't need this over here on the left. That was just a reminder of where we get the reduction formulas from.
Okay, I got you. So we got, then we get to where you were. So it's pi times 0. Pi times 1 plus cosine 2 pi. All right, I'm with you.
Okay. And now we have something that's quite easy to integrate. So we have the surface area equals pi. Well, the integral of that is theta. And the integral of this is sine 2 theta divided by 2. And so now we're going to take all of this and evaluate it between 0 and pi. Always have found it interesting when you have an expression that has just theta in it, plus a trig function. In a way, it just seems odd. I don't know why, but it seems odd to me. Always has. I always had to get by that step. Okay, so now if we plug in this for the thetas, we end up with pi times pi. Well, the sine of 2 pi is 0. So pi plus 0 minus 0 plus 0. Pi squared. You don't often come up with an answer of pi squared. Yeah, when you think about it, when you're integrating trig functions, the only time you're ever going to come up with an answer like pi squared is if theta is all by itself. Because normally, when you plug in the limits of integration into your trig function, you end up with numbers. You don't end up with pi.
I got you. Yeah.
Now, as I was mentioning in our last session, I'm a bit curious as to why my book doesn't at least address the volume of,
Yeah, right.
of objects that are revolved around, in other words, of planar objects that are revolved around some of the axes. You would think
Right.
volume would be significant, but what it caused me to start thinking about, well, where do they use this? Primarily, they use it in outer space, and they're more concerned with arc length. In other words, you want to know the length of the orbit of the Earth around the Sun. That's arc length.
Sure.
Once it can be expressed as a polar equation with the Sun as its focus, which is what we're going to do in about 5 minutes, is we're going to get into that. It's hard to imagine where it would be used for surfaces of revolution. I don't quite understand why we would ever need to do that, but maybe there are certain three-dimensional objects which are better described by a polar function being revolved about an axis, perhaps like a torus, maybe.
Seems like there should be some way to, I'm sure they have some way to do the volume.
Yeah, I can't quite imagine how you would do it. In other words, you'd have to figure out how to break it up. And disks, I don't know if disks are going to work. That's why I'd kind of like to see an explanation of it, is just out of curiosity as to how you take that three-dimensional object and break it up. And maybe that actually is covered in the next 5 chapters of the book. I don't know. But anyway, that is, we've got one more subsection left in chapter 10. And it is talking about conics and polar equations of conics. And that's because everything in the solar system seems like it either has elliptical orbits or hyperbolic orbits, or maybe even some parabolic orbits. I don't know if such a thing. I think a parabolic orbit does kind of exist now that I think about it. But this will help explain it. Just read a little bit about what they say here. In this chapter, you've seen that rectangular equations of ellipses and hyperbolas take much simpler forms when the origin lies at their centers. And you understand what they're saying there. If the center of an ellipse is the origin, then I can write it like this. Whereas if it's somewhere other than the origin, I have to write it like this.
Okay.
Which complicates the equation significantly. So, being at the origin, when we were studying conics, it did make it a lot easier. Well, what they want to do with these conic sections is they want to create the origin to be the focus of what is being rotated about. In other words, Earth has an elliptical orbit about the Sun, and here's the Sun, here's the Earth going about the Sun. It's not that big of an elliptical, closer to a circle, but they want to make the Sun be the pole or the center of the conic equation. Now, how do you do that is the question, and that's where it gets really complex. First of all, you remember the concept of eccentricity?
I remember the word. I don't remember exactly what it was. But...
Well, it is called E, and it is a measurement of the relationship between C and A, at least for ellipses and hyperbolas, we've studied eccentricity. And what this means is that a circle where a circle I believe has 0 eccentricity. Let's see, let me think for a second. Yeah, in other words, as we draw ellipses closer and closer to circles, I'll draw one here, it's just a slight ellipse. Well, C isn't very far from the center. That's C. And yet that's still A.
What were C and A?
C are the 2 focus points. Here, let me go back to this drawing here. Here's one focus. Here's another focus. And the distance from the center of my ellipse to that focus is C. And the distance from the center of the ellipse to the major transverse vertice is A. So as ellipses become compressed closer and closer to circles, eccentricity goes to 0.
Okay, and
if I have an ellipse that's like this, well, now here's the center of the ellipse, but C is much further out here.
I see.
And A is still that, but you can see that C divided by A would be closer to 1. In other words, the eccentricity for ellipses is always less than 1.
So C is the distance from the center to one of the focal points?
Yes.
And A is the distance from center to the edge of the ellipse?
Yes. So C always has to be less than A, which means this ratio is always less than 1 for an ellipse.
I see.
Okay. And the closer it is to 0, the closer that ellipse is to a circle. So the eccentricity of the Earth's orbit around the Sun is a very small number. If I remember right, it's something like 0.01 or something. It's not much of an ellipse.
So for a circle it would be 1, is that right?
No, for a circle it would be 0.
0?
Yeah, because as this ellipse gets closer and closer to a circle, C gets closer and closer to the center.
Oh, I see.
In other words, this ellipse I drew down here, C is barely away from the center. It's only in a very oblong ellipses where C gathers towards the edge, moves towards the edge. Okay? So for a hyperbola, C is always bigger than A because this distance is A. And since the focal points are always inside of the hyperbola, then by definition, A is always going to be less than C. So for hyperbolas, if E is greater than 1, always. And the relationship between this, let me think for a second here. As the hyperbola gets flatter, C gets closer to the vertice. So the flatter the hyperbola, the closer that would be to 1. So this might have just for example, that might have an e equal to 1.1, where this one would have an e equal to 2, we'll say. So that's the general relationship between eccentricity and the shape of either an ellipse or a hyperbola. Okay. All right. That's an important starting place. To lead in, let me see what else they say here. In this section, you will see that polar equations of conics take simple forms if one of the foci lies at the pole. Following theorem uses concept of eccentricity to classify the 3 basic types of conics. A conic with e between 0 and 1 is an ellipse. A conic with e greater than 1 is a hyperbola. And a conic with e equal to 1 is a parabola. It didn't say that a conic equal or an eccentricity of 0 is equal to a circle, but it is. I'm not sure why that's not needed. Let's talk about another concept that's part of this theorem that I'm talking about right now, classifications of conics by eccentricity. Let me draw their diagrams here. Let's see, if the center of my ellipse is going to be at one focal point, it's going to look like that. That's not the center of the ellipse, that's where C is. That's the focus at the pole. We're going to call that F. And that's going to equal 0, 0. Okay. And then we're going to find a point P on the edge of the ellipse. And then we're going to use the concept of directrix again. Now previously, when we've talked about a directrix, it's only been in relationship to parabolas. Well, now it's being more broadly defined. And there is a point on the directrix that we're going to call Q. And let me move that point down a little bit. This perpendicular distance from Q to P compares with P to F, in that PF divided by PQ is less than 1. Hold on a moment. Let F be a fixed point, focus, and D be a fixed line, directrix, in the plane. Let P be another point in the plane, and let E, eccentricity, be the ratio of the distance between PF and PD. So this actually is equal to E. And for an ellipse, it's less than 1.
So F was the focus, is that right?
Yeah. But notice that this is a completely different definition for E. We were just talking about E being C over A. Well, now they're defining E as no matter where this point is on the ellipse, I could have made it over here, the distance from the focus to that point divided by the distance from that point measured perpendicularly to the directrix is E also. Clearly they've done a bunch of, I don't know how they get this actually. I don't know how, in other words, this seems like such a different definition for E that I don't know how they went from this to this.
Now, what was a directrix again?
Well, previously, we only had directrixes when we had parabolas. And the concept, the definition of a parabola is a locus of all points equidistant from some focus and the directrix. In other words, if I have a point right there, that distance is always equal to that distance.
I see.
And look what that distance is. That's our PF. And it's equal to the distance from that point measured perpendicularly to the directrix. That's PQ. And by the definition of a parabola, that's also E. And since the definition of a parabola is those have to be the same, then E is automatically got to be 1 for a parabola. In other words, if I take this diagram for an ellipse and transfer it over here, there's F, there's P, and there's Q. And we certainly know that, if I put P up here, then this distance has to be the same as that distance. And it's always the same for a parabola. So for a parabola, we've never talked about eccentricity before. But since we're taking polar equations and turning them into where the center is at the focus, that's why we have to change our definitions about E. Or not change them, but in other words, this concept of directrix also applies to ellipses. It basically, there's a different definition for an ellipse. The true definition for an ellipse is the locus of points where the sum of the distance to the two focuses is a constant. In other words, if I have an ellipse like this, and I have two foci, and I want to take any point on my curve, well, that plus that is a constant. And it doesn't matter where my point is. If I had a point up here, that plus that is the same value as in this case here. In other words, it doesn't change. It's always a constant. Okay. And so
the definition, how can you have a directrix though there if PQ is not the same as PF, then all the points aren't going to be equidistant, are they?
They're not supposed to be equidistant with an ellipse. In fact, PF is always less than PQ. And that's why the eccentricity ends up being less than 1, is because the numerator is always less than the denominator.
But what is the definition of the directrix then? Because in the parabola it defined it as what makes PF and PQ equal to 1.
Right. Well, let me give you the entire theorem. Classification of conics by eccentricity. Let F be a fixed point, parentheses focus, and D be a fixed line in the plane, parentheses directrix. In other words, even for a parabola, this is just an imaginary line. But it's required to define the parabola. In other words, the definition of this parabola requires this directrix. You wouldn't be able to define something as being a parabola without this definition.
Okay.
Well, apparently, another definition for ellipse, other than a locus of points whose sum to the two focuses is constant, it appears that there's a second definition which says if you have this imaginary directrix, the distance from one focus to a point on the circumference of the ellipse is always less than the distance from that same point measured perpendicularly to this imaginary directrix. Okay? So these directrixes are merely for definition, I guess.
So really you could draw that directrix, say, farther away.
Well, I don't think so. No. With a parabola, the directrix is fixed. It has to be the same distance from the vertex of the parabola as the focus is. In other words, I didn't try to draw this right. This distance from there to here equals the distance from here to here.
Yeah, I mean in the case of the ellipse there.
I don't know about that. Yeah, I'm not sure, to be honest, whether I can draw that directrix arbitrarily anywhere I want. In other words, could I have drawn it over there? That's what I'm wondering. Yeah, maybe. In other words, as long as I draw it to the left, it forces this to still be true, right? Yeah. Whereas if I took this directrix over here with the parabola and I moved it down, it would not be true anymore. I can't move the directrix down. So I haven't figured out yet whether we can move this directrix. I kind of suspect not, even though it doesn't appear that it would violate this definition, the Conex definition. You might even move it to the right as long as it's still less than 1, you know. I don't think you could do that. In other words, if I were to draw the directrix right there, notice that the distance from P to the directrix is a lot closer. And yet the distance from P to F hasn't changed. Might still be less than 1. Not anywhere on the right, but just up to the certain point where it's still less than 1, yeah. It's still less than 1 as well. Yeah. Well, I would be surprised if we can move that directrix. Seems like it would have to be defined by something. Possibly. I bet its location is defined by the eccentricity of that ellipse. In other words, in the same way that the location of this directrix is defined by the steepness of that parabola. If I have a steeper parabola, the directrix is further away because the focus moves up, like that. So the eccentricity of the parabola determines where the directrix is. And I'll bet it's the same here. The location of this directrix. I don't know. We may answer that as we get further into this section. And let me draw their diagram of the parabola, merely because they use the same concept. In other words, we're putting this on a polar coordinate. Well, a polar coordinate, they wanted to use a horizontal parabola. I don't think it matters. It's going to be the same thing. And of course, the directrix, even pre-calc, the directrix is always there, outside. And there's Q, there's P, and there is F. And PF is equal to QP. So PF over PQ is equal to E, which is equal to 1. I'm thinking for a second. In other words, we can only have parabolas when E is equal to exactly 1. And that's why that directrix is fixed. With the case of an ellipse, E has to merely be less than 1. Which means, I'll bet anything, the location of this directrix is determined by the value of E. In other words, a more oblong ellipse like that, the directrix might be further or closer to the ellipse.
I see. So you obtain E.
Yeah, that ratio
is independently in some other way, and then set PF over PQ.
No, I believe that E is oh, I see what you're saying. Yeah, if you are given the directrix, then you can calculate E by this calculation.
Right.
If you're not given the directrix, then you need E to be able to come up with where to put the directrix.
Yeah, that's what I was kind of thinking.
Yeah. And then finally, don't have enough room here. Let me take away the parabola, just so I have enough room to put the hyperbola next to the ellipse. And again, we're going to start with a polar coordinate system where that's pi over 2. And this is 0. Same thing over here. Yeah, that's same thing over there. Remember, we're on the polar definitions of these conic sections, so we need a polar grid. And let's see. I want the focus. Oops, excuse me. I want the focus of the hyperbola to be there. So that's always F in all of these drawings. Here, P is there, and the directrix lies there, and if I put a point Q for this one, PF over PQ equals E, and it's always greater than 1. In other words, this distance there is always greater than QP, or PQ. And that's measured from either part of the hyperbola. In other words, if I want to measure this and put my point, another point, I'll call P prime, well, P prime F in other words, let me add one more thing here. I've got PF over PQ is the same as P prime F over P prime Q prime. Why is it a different Q? I didn't draw that right. There's Q prime. Okay, now I get it. In other words, if you're on the side of the hyperbola that is not contain the focus that's the center of our polar curve, then it's still a point on this hyperbola to the focus of the other half of the hyperbola divided by p prime to this new q prime. This q prime still lies along the same directrix. It's just different, in a different place vertically. And that's all equal to E. You know, interestingly enough, they don't say that in the book. They say that they put everything but the E in both of these. They leave out E. And yet, in the definition, they say that that is E. Let P be another point in the plane, and let E be the ratio of the distance between PF and PD. So they've definitely, in the theorem itself, stated that the ratio of PF over PQ is E. That is a new definition for eccentricity. And same thing with hyperbola. All right. Now, let's briefly mention the four formulas that are going to be key. If I have a polar equation of this form,
Is that a D?
Yeah, it is. And I'll define each of these in a second. E is the eccentricity, and D is the distance between the focus at the pole and its corresponding directrix. In other words, D is the distance between the focus at the pole and its directrix. So D would be this.
Focus at the pole.
Mm-hmm. Or from here to there. In other words, D is neither PF or PQ. D is just the distance from the focus of the pole to this imaginary directrix that is used to define E. Okay? Go back to these two equations. This, if you have a polar equation that is in this format, it's a conic. If E is greater, where E is greater than 0. E has to be greater than 0.
Now, when they say R, that doesn't have anything to do with radius, or?
No, it doesn't. R is their polar equation. I could also call this F of theta.
Okay, I got you. Seems weird that they would have decided on the letter R for that.
I agree, but in the polar grid, remember that if we have a polar equation, R is that distance right there.
Oh, I see. So it does.
Yeah, it has. It's like radius, but it doesn't have to be. In other words, it depends. If you have a centroid, you wouldn't call that the radius. Oh, I didn't draw a centroid very well. It's just the measurement. R is the measurement from the pole, from this, whatever it's called, pole, I guess, to the edge of the curve. Whatever my curve looks like, whatever that is, that's R.
That's right. Okay.
Okay. And when you define polar equations, our equation of a circle was r equal cosine of theta. Well, that defined this polar graph. And r is always this distance, or this distance, or that distance. It's not really a radius. I think part of the problem with math is they simply ran out of letters by the time they got through the 26 letters of our alphabet and the Greek alphabet. They end up having to use letters repeatedly. It annoys me that E has these two different definitions. E is eccentricity, but E is also 2.71, the limit of 1 plus 1 over x all to the x power as x goes to infinity. That's the other E. Well, I guess we have to live with that R being different things.
What was the definition of E, the other one? I just briefly.
Limit of 1 plus 1 over x to the x power as x goes to infinity.
Okay.
Classic problem that usually when I'm trying to inspire math students, in fact, I'm sure I did this first time I saw you, was talk about this. That's equal to 2.71 and change, or E. Okay?
Yeah.
And the cleverness of this problem is that as x goes to infinity, the part in the parentheses goes closer and closer to 1, right? Because this term goes to 0.
Right.
But this gets bigger and bigger and bigger. So you might start out with 1.1 to some big power, and then you got 1.01 to some bigger power.
See, this is where I would get confused in calculus in a sense, because in the limit, that seems like in the parentheses it goes to 1,
Correct.
and 1 to infinity power is still 1.
That's why this is such a good problem. I refer to this as my Superman problem. In other words, there was a Superman edition where he wanted to go back in time, and the way he did it, he had a clone of himself, and one Superman stood firm, immovable, and the other Superman flew directly at him at a certain speed, unstoppable.
I got you.
What happens when you have an immovable object meet an irresistible force? Well, in the Superman, he goes back in time. Because you can't, that's a paradox. You can't, first of all, have an immovable object meet an irresistible force.
Right.
Well, this is headed towards 1, but this is headed towards infinity. So you might think that the answer would have to be 1.
Right.
But plug this in, try a bunch of these into your calculator. If you did this, 1 over 100, and raise that to the 100th power, that's going to give you a number very close to E. And then every time we up that and up that, is all we're doing is adding more significant digits onto the number. So E can be calculated out to 1,000,000 digits quite easily.
I mean, it seems like I've seen problems where they would have that be equal to 1. You know what I'm saying? Like,
Well,
I don't know. Maybe I'm wrong about that. I guess.
I don't think so. I mean, this is pretty fundamental.
Yes, maybe I've just seen it without the.
What is interesting about this
and the exponent?
This expression 1 plus 1 over x to the x power is the way much of nature works.
Right.
In other words,
I've probably seen it with a finite. Now, if x was instead of x, they put any finite exponent there, like say 5 or something.
Right.
That would be 1, right?
No. If I put in 5, you got 1 plus 1/5.
No. I mean, instead of the second x being in the exponent, you got the 1 over x.
Oh, yeah. If I take that away like that, yeah, that's 1.
Yeah.
For sure.
And regardless of if you put any finite number as an exponent there.
Right. What we're talking about here is basically the indeterminate form.
Right.
In other words, this is a little bit like 0 times infinity.
Right, I see.
Or even, no, you can't use 1 because that's not indeterminate. 1 to any exponent is 1. But 1 plus change, in other words, this never actually reaches 0. So even when x is a googol, you've got 1 and a little tiny bit, and that little tiny bit, the fact that we're exponentiating it to a googol power, makes the number more than 1. The amazing thing is that it settles on that. Because if you were to ask somebody who didn't know the definition of this, e, well, what number is this thing going to go to? What is that limit as x goes to infinity? There's actually a way to solve it, proving that it's e.
Yeah, no, I'm sure that's right. But what I'm saying is, like, if you said instead of that second x, you put any number there, 5, 7, whatever, then you would say the limit of that is 1, right?
Yes.
That's what I mean. So they both say that the limit of the thing in the parenthesis, I guess it's which do you do first, you know what I'm saying? But they use
it all comes down to whether your variable is in the exponent or not.
Yeah,
the fact that the variable's in the exponent makes all the difference in the world.
Right.
Because
it can't
change also. Yeah. In other words, as x gets bigger, it gets bigger.
Yeah.
But
so in the case where it's
this concept. Go ahead.
In the case where in the exponent, they use the logic that it goes to 0 when there's an exponent. I would just say it seems like they both do and don't use the. Because in one instance, it's always 0 and change. In another instance, you say it's 0. I mean, it's 1 and change.
If that is a constant, no matter how big, then this limit would be 1.
That's what I'm saying.
But as long as it's a variable that it continues to rise as x rises, then the limit is 2.71. Now, why is e such a key number in our universe? I mean, it's right up there with pi. In fact, it's between e, pi, and the golden ratio. I cannot think of any other numbers that are special.
I guess this is the main thing that I was thinking of is that in the part within the parentheses, it seems like in calculus I've seen it used as that's always going to be 1 and something, but I've also seen it be used as that's just 1 because the something vaporizes.
Right.
And it seems like in different contexts I've seen it used in different ways.
I've done the calculus proof. I might have even done it with you on proving that this goes to e. And
I'm sure that one goes
what you do is you let it equal f of x, and then you take the log of both sides, which allows you to take that x and put it down in front.
Okay.
Then you
I'm not disputing that in this case it goes to 2.7. I just meant in all kinds of different applications. It seems like sometimes they use the notion that like just the part in the parentheses, it's 1 and something. And sometimes they use the notion that it's just 1 in the limit. You know what I mean?
This is what comes out of anything that grows or decays based on the amount of quantity there is.
Yeah.
In other words, population. Population will grow based on how much it grows. The rate of change of the growth is a function of how much there is there. The same with decay. I'm not sure if it's the rate of growth or decay or the amount. But anyway, that's where, since so much in the world does that, behaves according to the amount that's there, this ends up being probably the second most important number in math after pi, is this limit. And e, that's why e is in all of these differential equations and continuous growth. Remember, if you have money earning continuous growth, it's e to the RT. If it's continuously being compounded, you end up with e. Anything that is compounded based on the amount that's there ends up with the limit of 1 plus 1 over x to the x power, which ends up coming out as e.
I think continuous growth or decay, I guess, would involve e.
Well, and it actually comes in, there's the chapter on differential equations starts out with that. And it's been a while since I've looked at it, though, so I can't explain it super well right now. But
that's fine.
Anyway, this is not the same e as this.
Yes, I got you. Okay. Now, those equations at the top, you said those were if the function of theta is a conic section, they have to correspond to those?
Well, if you have a polar equation that looks like one of these, it's a conic.
It's conic, okay.
Yes, where e is greater than 0. And e is the eccentricity, and d is the absolute value, or the absolute value of d is the distance between the focus at the pole and its corresponding directrix. Okay, so this is going to give us ellipses, hyperbolas, and parabolas. Not circles, because e is 0 for a circle.
Okay, ellipses, hyperbolas.
Okay. And that's where we'll begin next time, is dealing with some polar equations and graphing them based on various things. And we'll also talk about Kepler's laws and things like that.
Oh, okay. Sounds good.
Okay.
Astronomy and whatnot.
Yeah, no, I find that enjoyable also. I'm wondering whether it was the only reason polar equations were invented, so that they could study these conic sections that have to deal with the paths of the planets. I'm just curious, is that if we lived on a planet all alone in the universe, whether we would have polar equations.
Oh, I see what you mean. Yeah. Well,
are there other applications other than that? Yes, probably, but
yeah, maybe electrons or something around.
Possibly. I don't know. We'll find out.
Okay.
All right, Timur. I will talk to you next time.
Okay, thanks so much, Dave. We'll talk next time.